So once we're done with this next part of the lesson, we will know how to look at a rational function and figure out what it's probably going to look like. One important note here is that every rational function wants to be a polynomial. It's trying to be a polynomial, and you'll kind of see what that means. It's very informal, but if you think about it that way, it's very helpful. Let's start by looking at some examples, actually. Number 4 is purely just looking at examples, but I did say, take note that the second function g of x for each one of these forms a boundary for the rational function that's included here. This brings us to an important fact. These boundaries we're seeing are actually non-vertical asymptotes because, again, the graph gets really close to them at certain points, right? But it doesn't actually perfectly get there. And they're actually found by dividing. And let's take a look at an example. We're going to revisit the same problems we just saw, or same functions. Divide each one, identify any vertical and non-vertical asymptotes. I'll do the division for you. Let's just look at each one. Here's the first function in part A, and I'm color-coding things to help you remember how we extract that information. So the denominator, whether it's this part or this part, that helps us figure out the x values that form the vertical asymptotes. And you remember, whenever that makes this undefined, assuming we haven't canceled it out to make a whole, then we have vertical asymptotes. So here we have x equals -3 or +3 is where there's a vertical asymptote. But once we do the dividing, here's the crazy thing. The quotient, so if you ignore the remainder, that quotient right there that you get when you do dividing, that actually forms the non-vertical asymptote. So my non-vertical asymptote is the equation y equals x. That's really cool. Let's take a look at part B. So for this one, notice that these two are equal degrees each other. So when you divide them, it's just going to be a constant. That makes sense. Whereas this one, this is degree 3 over degree 2, so it should be linear when we divide it. So we kind of know what to expect when we do the division. And so again, this remainder for now, that's just kind of creating that extra weird error that's happening. So vertical asymptotes, again, what makes the bottom equal to 0? And in this case, it may help you to actually factor the 2 out, and then in parentheses we have x squared minus 4, and then you can see, oh, okay, that's -2 or +2. So again, we know x equals -2 or +2. Those are our vertical asymptotes. And then we have another asymptote at the line y equals 3. Okay, on to C and D. So again, if we do the division, we can see what's going on. What makes the bottom 0? Again, I'm just telling you nothing cancels out here. So the vertical asymptote happens when x equals -1 for this one. Where's the other asymptote? Again, that's the quotient we get when we do the division, right? Ignore the remainder. And so y equals x squared minus x plus 6 happens to form the other boundary, the other non-vertical asymptote. Now this one's kind of funny, this last one. This doesn't even divide at all, right? Because it currently isn't even big enough on the top. And so technically that's 0 plus the same thing we had. And so the non-vertical asymptote here, there still exists one, but it's just right there at y equals 0. Now, interestingly, we saw that this didn't have any vertical asymptotes, and you can clearly see here that there is no real number that will make the bottom here equal to 0, because this is +1. And so I can just say, well, there are none. There are no vertical asymptotes. Now we're really ready to take a look at just being given a rational function. Now you're ready to just be given a rational function and then analyze it a bit by finding its vertical and non-vertical asymptotes and then taking a guess at what the graph might look like. Alright, so we've made the procedure pretty nice and simple. Just so you know, in most courses where you graph rational functions, I think it's made way overcomplicated. It can be really simple the way we've learned it. So, to predict the graph of a rational function, now you notice I didn't say sketch it by hand completely, because I don't need us to be able to fully sketch by hand, okay? But to be able to pretty much have an idea of what it's going to look like, here's what we can do. identify and draw any asymptotes. So that means vertical and non-vertical, okay? And you gotta remember from before how we get each one of those things. And then what we can do is just plot some points in the resulting regions to get an idea of where the graph is gonna be and take a guess at the shape. And then you can, of course, certainly just check using a grapher to see how you did. Now, one thing I put on here is watch out for holes. Remember that if it factors out and two factors cancel, there ends up being a hole. So let's use this to transition into our last example, and we'll have multiple problems in this one. First of all, predict the graph of this function. Now, I was a little lazy and I made it already factored for us. Maybe we'll look at another one that we need to factor, I guess, or at least think about if it factors. And you can see that it does share a common factor on the top and bottom. So since we noticed that cancels out like we learned previously, this means 2x minus 9 over x minus 5. But we have to make a special note here for a moment that there is going to be a hole at x equals -1. So just keep that in mind for the future. Now what we can do is fully identify the things. Now before we actually do anything, it's probably good that you remember we need to actually do the division on that. So if you do the division, we get 2 plus 1 over x minus 5. So right, this is the remainder. And since this did not cancel out, remember that tells us our vertical asymptote is when x equals 5. And this right here, y equals 2, represents our non-vertical asymptote. So it turns out there's a vertical one and then one that's horizontal. Let's then take this information and begin our sketch. So here's the divided form. We have found that there's a hole here, a vertical asymptote here, and then a non-vertical there. So I've sketched my vertical and my non-vertical asymptotes. Now this hole at -1, I can't really do anything with that yet. One thing to mention, when I said plot some points and then in the different regions, notice right here this vertical asymptote splits it into less than 5 or more than 5. So we're going to have a piece of the graph here and then another piece here. Now this horizontal asymptote's weird because we can't have a piece here and a piece there. That wouldn't be a function anymore. So you're either going to have a piece of the graph right there, or else you're going to have another one down, or else it's going to be down here. And same on this side. It's either going to be here or here, but not both. So what we can do then is just make a table of a few values that are maybe a couple numbers down here and a couple numbers up here, and then get an idea for what we think is going on with the graph. Now I was a little bit strategic with how I chose some points. I chose a couple that hug kind of close to the vertical asymptote because I know it's going to either shoot up or shoot down there, and I want to be able to get a good, accurate sketch of the graph. And then just a few other ones that are, kind of spread out below and above. I did choose 4 and 6 just because both 4 and 6 will divide nicely with 1 because they make this either 1 or -1, so it'll make this a whole number. So it's good to be strategic kind of with your choices, but in the end it doesn't really matter that much because as long as you get a few points you can be like, okay, I think I know what's going on with this graph. So I've got our points plotted here and here, and it seems like we got a pretty good idea of what it's going to look like. Don't forget the hole at -1 though. So here at -1, since we figured out there's going to be a hole, I'm going to put that approximately where it looks like the graph will be. And remember, because there are asymptotes, we know the graph hugs towards those asymptotes. So we kind of draw it in to make it do that. So there's one part of this, and then this one's going to come up there, and then down there and hug that. And we got our graph. And of course, you should always check with Desmos later. All right, so here's one for you to try yourself. G of x equals x squared plus 8x plus 8 over x plus 3. Now, I'll just let you know right off the bat here, this x squared plus 8x plus 8, it doesn't even really factor, I don't think, at all, but especially it does not have an x plus 3 as a factor, so there's no holes in this one or anything. So you can just identify all the different types of asymptotes, check some points, and see what it looks like, and then we'll check it together. Go ahead and pause now. Okay, so I have my vertical asymptote. And my non-vertical one this time is linear, but it's not horizontal, at y equals x plus 5. I've plotted some points. Again, you don't have to have done the same points as me, but it is nice to have some that hug a little close to the asymptote at -3, the vertical asymptote, and then spread them out a little bit. And then I took a good guess at this graph, which if you check Desmos, you'll see really is a pretty good graph for that. So that's pretty much it. The thing is with these, there's so much variety in the shapes, you can't just generalize, oh, this is going to look like this and this is going to look like this by looking at them. So this procedure is a nice, powerful tool to use for any rational function that's thrown at you, and you can do this and take a good guess at what it's going to look like. Let's take a look at just one little interesting variation on this one before we wrap up for today. So I always like to ask what-if questions. We can kind of call this part C if we want. But you notice that this remainder here was a -7. What if it had been a +7? And those are always good mathematical questions to ask and see what changes. But this goes with something we said before. Subtle changes can make big differences. So what's going to happen is this wouldn't be a +8 here anymore in the original one. It would actually be a +22. And again, we said we made this positive instead. The interesting thing is, our non-vertical asymptote wouldn't change if we went from here to here, and neither would our vertical asymptote. So the boundaries are exactly identical. But if we actually plot, let's just use the same points you used before, and plot some outputs, watch the difference in the two graphs. So interestingly, after plotting some points, my points weren't perfect, I could have done more, or just checking Desmos, of course. It's crazy. What happened with that little change was, instead of the two pieces being in these regions opposite each other, they switched to being in these regions opposite of each other that were empty before. So again, it's really crazy how these things behave, but now you have all the tools that you need in order to predict what the graph is going to look like for any rational function. So that's it for today's lesson. Again, happy math, and we'll see you guys next time.